Alrighty, so today we're going to have a look at the Circular Motion Lab and your results. Now, I haven't had a chance to sort of look at what people handed in, and maybe some of you haven't handed them in. That's fine. I guess you actually get a chance here to check to see if how your answers match what I've got. Okay, so you don't need to draw any of that. What I would suggest to you, though, is these are kind of sort of notes. We're going to come up with some formulas today. So you might want to jot some things down as we go. So what we're going to do is we're going to take the results of our experiment. We're going to derive some formulas that relate centripetal force Fc to various aspects of UCM. UCM, of course, stands for? Uniform circular motion. Now, the uniform means that the speed remains the same. Right? The speed remains the same.
No, these are just the 3 pages all the way to the back.
I don't know. Okay, so the first one that we did when you took the one-stopper apparatus and you actually adjusted the number of washers on the bottom, right? So what we did, just so you have an idea what we did here, we've got a glass tube, we've got rubber stoppers on a string, and on the bottom here we put washers. And we spun it around, and we measured the time it took to go around, and we added more washers to the bottom, and that meant more force pulling down, which meant the centripetal force was greater. And we timed it and decided what happened to the period as we went around. Okay, so when you graphed period squared versus FC, your graph should have looked similar to this. What was your shape of your graph? It was like man. I'm not sure what sound that makes, but that's the sound. Yeah. Yeah. Ski slope. Okay. So I'm hoping that everybody sort of kind of got that. Right? I got some fine print here. Let's just see what that says. This suggests that it may be an inverse or inverse squared relationship. To confirm, we're going to graph t squared versus, and it's missing. But good thing I happen to know what it is. So what I had to do next was I had to graph t squared versus 1 over fc. Do you remember doing that?
Yes.
Okay. And in the good old days, in the pre-calculator, or graphing calculator, pre-computer days, that's how you actually figured out what the actual relationship was. You guessed, and if you think it's 1 over fc, and you get a straight line, then that sort of proves that that's correct, that it's an inverse square. Okay, so we got that. And then when you graph the next one, did it straighten out? What sound did it make, Stefan? Very nice. All right, so this suggests that the relationship between them is t squared is proportional to 1 over fc. That's an important part. T squared is proportional to 1 over fc. In other words, the square of the period changes inversely with the centripetal force. In other words, the more washers you add, the bigger the denominator, which makes the whole thing smaller, which makes the period smaller, which means that it goes faster. Is that what you found, Kyle? When you added more and more washers, it went around faster? You should. Okay? So it goes faster when you add more centripetal force. Okay? It goes faster. And remember, when it goes faster, the period actually goes down, right? The period goes down when it goes faster, because the period is how long it takes to go around once. Okay. So t squared is proportional to 1 over fc. So that was part A. That's the relationship that you should have got from part A. And I think for the most part, everyone got that. Okay, in part B, or number 2, we looked at the period versus the radius. This is the one where you change the length of the string, right? And what did you find when it was a shorter one? It went? Periods were shorter? I think you should have got a straight line there. Did you? Which meant that the bigger the radius, the bigger the period, which means it's going slower, right? Bigger period means slower. Okay? The bigger the circle, the
Faster.
really?
Wouldn't
it go the same speed? It just
takes longer to get. Yeah.
Isn't that speed? Takes longer to go around?
No, it's just.
So it's going the same speed, but in a shorter distance.
Did you not get that relationship? Did you not get a straight line graph when you did? Kind of? That's what you got in? Yeah. So this tells me that this period squared, whoops, t squared, this is the radius. So when the circle got bigger, the period got bigger, which means it's actually going slower. Think about it. It's going, right? We'll make a sound effect there. But when you go big, it's going.
It's only got pretty toes to it.
The radius gets bigger because it, like the string gets longer.
Stop for the speed. It just, it takes longer to go.
You'd think so, but no. The math tells us there's the relationship. You got it. You graphed it, didn't you?
Oh, yeah.
Oh, not yet, he says. This implies that t squared is proportional to r. Okay? The period squared is proportional to r. In other words, the bigger the radius, the bigger the period. This was part B.
Bigger radius.
No, it's going to be 1 over FC because it's equal to R.
Okay, bigger radius is.
T bigger radius means bigger period. Bigger radius, bigger period. Period versus mass. Now the third one that we did, Zoe, was we added more and more rubber stoppers to the end. Okay? And you can probably just barely see it there. Did you get a straight line for that one? That's the one that we don't always get the perfect results, and that's usually because the string length is different. But you should have got a straight line. In other words, the more rubber stoppers, the longer it takes, which means it's going slower. In other words, t squared is proportional to m, right? The bigger the mass on the end, the slower it goes. Imagine if you got like a big heavy brick or something at the end. It's going to go pretty slow, isn't it, right? Get a little tiny marble or something rather than the end. Fast. That's part C. All right, so now Stefan and Quinn are already predicting. You've probably seen that I've had t squared on the left-hand side, and now I've now made it proportional to 3 different variables. So now I'm going to put them all together, dump them all together here. So I'm going to combine our proportionalities together, and I'm going to see that t squared is proportional to rm over fc.
I agree.
We're not done yet.
You're done. No, you're not. Just say that.
T squared is proportional to rm over fc. Now, if I were to make that into an equation, to make it into an equation, you remove the proportionality and you insert the letter K.
K is for something.
K is for constant.
Yes.
Nicely done. K is for constant. K is called the constant of proportionality. It's the number that makes it work. In an equation, in a proportionality, like I'll get to Quinn in a second. If I have something like A area of a circle is proportional to the radius squared, when you change it into an equation, you put a constant in there, and A equals pi r squared. The number pi is the constant of proportionality. It's the number that makes it work.
Is that going to be a given constant?
It is, but first we're going to have to find it. Quinn has a question now.
Why are you using equal to n then?
Because you can get proportionalities from the shapes of graphs, but once you want to actually work with it, you need to make an equation out of it. To make the equation work, you need some magic number that makes it work. Like, what's the number if I put in half a meter for radius and half a kilogram and so much centripetal force in newtons? What's the period going to be? Like, how do I know what the number is going to be? I need a number. In other words, I'm going to have to come up with what's the number. It's like Avogadro's number, yeah. It's a magic number that makes it work here. 6.02 times. Yeah, I think you're right.
What's that? Okay, what's that? What? What's that?
Okay.
Is that like moles?
Now, for the most part, we like, for whatever reason, we like having F on the left-hand side. All I've done here is I've just switched my t squared to my F, right? Okay. So that's the formula that we get from our lab.
Okay, cool.
The problem is we don't know what K is. Now, we could solve for K. We have values for R.
Google it.
We have could we find values for M? It would just be the mass of the stoppers in kilograms. Could we find values for T squared? Sure we could, right? Could we come up with values for centripetal force? Yeah, we would just have to weigh them and then convert. We could do it. We could. I don't know how accurate it would be, but we could. We could. Well, that's what we're trying to get, right? If we knew all these values, if I knew an F and a T and an R and an M, I could solve for some K value, right? Would we get like consistently K across? We'd probably get close, right? We'd probably get close. Is there another way? And the answer is yes. Okay. So looking at these two formulas, FC is KRM over T squared, comparing that to FC equals MAC. In other words, Newton's law, F equals MA. Talk about it in a centripetal sense. So centripetal force is equal to mass times acceleration when it's centripetal acceleration. Okay, so you can see here, I've got my M, I got my M. So what's my AC going to be? When I take the M out here, I'm going to have KR over T squared. Right? So this is our predicted formula for centripetal acceleration. Right? Basically, all you're doing is just taking the M out. Okay, I have not yet begun to dazzle you with formula derivation. That's just the preamble. That's just the warm-up. The once around the gym to kind of get yourself going.
I'm not ready. I'm not ready.
We're going to attempt to, do you have a lap?
No,
We're going to
call this question, man.
attempt to derive a formula to see if it matches our prediction and to determine the value of K. Now, make a little bit of prediction here. We've got something going around in a circle. What do you think is going to appear somewhere?
Force and norms.
Acceleration.
What number or what symbol did you know? Pi.
Oh,
It's a circle, man.
I said
Circle. Okay. Now, here's where things start to get a little bit more complicated. I will try to slow down a little bit here. Am I good to go? Okay. You know what? I'm just going to let you copy that. All right. So we're going to start by looking at speed and period. In one complete revolution, the distance traveled d is the circumference as it goes around the circle. The distance traveled is circumference, which we already know is 2 pi r. And the time it takes to do this is our big T, which is our period. So given this, we're going to write the formula for speed, and we're going to substitute, right? So v equals d over t. In this case, that's the circumference over the period, or 2 pi r over t. And then I take the v and the t, and I just sort of do a flip-flop there. I got t equals 2 pi r over v. And all I've done there is I've taken a couple of old formulas and sort of combined them together. And I'm going to call that equation number 1. Pardon me? 3 or 4 anyways. Equation number 1, because I'm going to say, in the future, I'm going to say, remember back to equation number 1, let's plug that in here. That's why there's a box around it. Okay, because I'm going to come back to this one. Saved equation number 1. The period is 2 pi r, 2 times pi times the radius divided by the velocity. T is the period of time it takes to go around.
Yeah, small t is time. Big T.
Yeah, small t is time, big T is the period, once around. Okay, now, centripetal acceleration. Centripetal acceleration. So the formula for acceleration is A equals D. You've known that since about grade 10. We're going to just rearrange that a little bit to give me delta V is equal to A delta T. Now, in the past, I've sort of allowed that delta to sort of disappear. Let's hang on to it today. Okay, so delta V is equal to A delta T. And for an entire revolution, all the way around, my delta T is big T, which is the period. And I'm going to say my delta V is delta VT. I'm just going to put a capital T on delta V just to signify that it's the change in velocity for one revolution. Okay, and now I'm going to save that one as equation number 2. Delta VT is equal to AT. And pause for a moment. Here we go. Okay, now, don't start writing. Just put them down.
Tangents.
Just listen. Just listen here. Another way to think about delta V for a whole revolution. Suppose several instantaneous velocities are recorded and they are shown as the tangent lines below. So here's, and look at the black one. So I've got V1, V2, V3, V4, V5, all the way around, right? Just suppose. They're instantaneous velocities at a variety of locations. Okay. Each vector V1, V2 is the same length. How come? Because the speed is constant, right? The length is the same, the angle is not. The value in red, delta phi, is the difference between V1 and V2 and so on. So the difference, how much does the velocity change? Well, it's vector subtraction. It's from there to there. So my red value here is my delta V1. There should be a triangle there. So delta V1, delta V2, and could you draw those all the way around if you chose to? You could. You could. All right. Now another way that we can do vector subtraction is to place vectors tail to tail. So the black ones, once again, are, this would be V1, this would be V2, this one is V3, and so on. Okay, so if I place them all tail to tail. And then the red ones here, this is delta V1, delta V2, delta V3, 4, 5, 6, and so on, all the way around, right? You'll notice that they sort of, kind of make a circle, right? Now, if I were Joy, if I would, rather than just take, how many have I got here? 1, 2, 3, 4, 5, 6, 7, 8. I have 8 black vectors, instantaneous vectors. If I were to say take 100, right? Instead of V2 being down there, what if V2 was like right there, and V3 was right there, and V4 was right there? Then this one would have a whole bunch of black ones, and the red ones would be much shorter because the time difference would be less, but it would be much more circular. And if you sort of extrapolate that to like 1,000 or 1,000,000, well then eventually your red ones become a circle, right? And that's sort of a calculus idea there. So in this fashion, delta V1, delta V2, etc., for a circular pattern. The total change in velocity, delta VT, is the sum of all the little red ones. Delta V1 plus delta V2 plus delta V3, and so on. And again, if I got a whole whack of them, they're very circular. Now, this should read 2 pi r.
Well, so the red ones on the left side, because it's going to the left and down, would they be negative?
No, they would just have some directional, like 10 degrees south of east or something, right? So I've got the total change in velocity is the total change. Mary, you need to listen. The total change in velocity, delta VT, is the sum of all the red ones, delta V1 plus delta V2, and so on. They make a circle. They make a circle, right? And because they go around, it's a circumference. This is a circumference, right? Which is, the formula for circumference is 2 pi r. What is the radius of this sort of pinwheel circle? V1, V2, V3, right? It's the actual velocity, where the radius of the circle is V1, which is equal to V2, which is equal to V3, the speed part. In other words, delta VT is 2 pi V. That should be a pi. 2 pi V. Now, I don't know what you want to write down there.
Just that.
Is that like still part of the
It's still part. I've got 3 saved equations there. I'm going to go through that once more in a second here. So, Stephanie and Quinn have it right. Now's the point where we start putting things together. Recall equations 2 and 3, which were delta VT equals AT, and delta VT is equal to 2 pi V.
That wasn't part of the subset on its own.
Okay, so because they're both equal to delta VT, we can, exactly, sound effect boy, AT is equal to 2 pi V, which we can then get rid of that t or move that t and give us A equals 2 pi V over t. That's called number 4. This is called number 4. Now, remember equation 1, which said t equals 2 pi r over v. Similar, we're going to substitute equation 1 into equation 4 for t. In other words, we're going to take this junk and put it in there. And I think you see that there's going to be some canceling, right? Because you got 2 pi on the top, you're going to have a 2 pi on the bottom. If you like, go ahead and substitute that in. You're going to see it on the next slide. Not going to do it. You're going to wait and see.
Yep. I agree with Stefan though, but
You're going to be cautious.
yeah,
Excellent.
'cause I read in pencil. Exact opposite.
I think he's beaking you.
I don't know. It's just really easier. It's read in pen, it would make more sense to read in pencil.
Okay. So there's my 2 pi r over v. It's going in place for t right there. Stefan's got 2 pi v over 2 pi r over v. The 2's and the pi's cancel. The v goes up top. V squared over r. Is that what you got, Stefan?
Yes.
Yes.
Awesome. You're done. All that work for a chintzy little formula like that.
Yeah.
Centripetal acceleration is equal to v squared over r.
Velocity squared?
Velocity squared
Or
over r.
AC, or AC?
AC, centripetal acceleration, yes. Centripetal acceleration. Now, you can also do it this way, too, which sort of gives us another one. You could take the 2 pi over t and then multiply by v. Right? Instead of 2 pi v over 2 pi r over v, you could just multiply by v and then take, it's a sort of another substitution, right? This is the v here, right? Take 2 pi r over t, multiply, and then you end up with 4 pi squared r over t squared. These two are equivalent. You need both, yes. It depends on what you know.
What's going on here?
It depends on what you know. Those two are equivalent. Well, I took 2 pi over t, and I just took this v here, Stefan. I took that v and sort of put it out there instead, right? Instead of going 2 times pi times v divided by t, I went 2 times pi divided by t, and then times by v. And I took the value of v out of here, which was 2 pi r over t, put it in there, and then multiply. So these indeed are equivalent. This one you can use if you know the velocity. This one you can use if you know the period. So it depends on what you know. Now, here's where the magic happens.
More?
Yeah, a little bit. Here's where the magic happens. Those are in boxes for a reason. You need them. But we're going to use these. You're going to use those formulas. If nothing else, you need to know those. Where v is the velocity in meters per second, r is the radius of the circle measured in meters, a is the centripetal acceleration measured in meters per second squared, and t is the period measured in seconds. Now, think back about 20 minutes ago, where we had that magic k, special k. What's the value for k, you say?
Okay, Dr. Seuss.
Oh.
Dr. Seuss, put you back.
Okay, so what was our predicted formula based on the experiment from way back when we started? It was A equals kr over t squared.
Okay.
And we wondered what the value of k was. What did we just derive?
We derived this.
We got A equals 4 pi squared r over t squared. Those look kind of similar.
Wow.
What's the value of k?
4 pi.
4 pi squared.
4 pi squared. Right?
That sounds.
There's the r, there's the t squared, there's the r over t squared. What's left? The k? 4 pi squared.
Ah, yes.
So in other words, if we'd measured the mass of the rubber stoppers, if we'd actually found the time in seconds, measured the centripetal force of the washers, put it all together, we would have got some number that we would have had to realize is 4 pi squared. Would you have recognized some number? Oh, that's 4 pi squared. Of course not. Which is the reason why we don't do it. But if we did go back, we would get something close to that, right? It would. In fact, that'd be an interesting little thing to do sometime.
Right now.
4 pi squared is the value of k. Yes, I do. So, given, we're almost at last slide, promise. Given our formulas that we've now come up with, AC equals v squared over r, and AC is equal to 4 pi squared r over t squared. If we want a formula for centripetal force, these are accelerations, right? These are accelerations. If I want centripetal force, since F equals ma, Fc is equal to mac. These are already a's, so all I do is just add an m, right? I just add an m in there, and that becomes force. Fc equals mv squared over r.
So that's like the final one.
That's the one for force. The ones we just did in the last slide were for acceleration. They're almost the same, right? So this one's going to be the same thing here. To turn into force, I just have to put a mass on that side, right? In other words, to get centripetal force, just multiply by the mass. It's really not that.
What's the first one? Is that AC?
They were AC, right? And then I made them into force by putting masses in there, right? To make them into, ignore these. I just use those for demonstration purposes, right? So these are my formulas for acceleration. To turn them into force ones, I just multiply by
6.
m, mass.
You're always supposed to answer 6.
Plug an m in there.